All right, let's go.
Number 10. The fourth spatial dimension, the direction you cannot point to. There is a direction you cannot point to. Not up, not down, not left or right, or forward or back. A direction completely perpendicular to all three of those simultaneously. Mathematically, it exists. Physically, we have never observed it, but the math does not care. In 1884, Edwin Abbott Abbott, a school teacher and theologian, wrote a novella called Flatland. The main character is a square living in a two-dimensional world, flat, no height. He cannot imagine up or down, they do not exist for him. Then a sphere passes through his world. To the square, it appears as a circle that grows from nothing, reaches a maximum size, then shrinks back to a point and vanishes. The sphere existed the entire time. The square could only perceive its cross-section. We are the square. A four-dimensional object passing through our three-dimensional world would appear as a three-dimensional shape that morphs, changes size, and vanishes. We would see the shadow, never the object. The fourth spatial dimension, called the W-axis by mathematicians, is fully describable with equations. The four-dimensional equivalent of a cube is called a tesseract. It has 8 cubic faces, 24 square faces, 32 edges, and 16 vertices. You can calculate all of these. You cannot visualize it. Your brain was not built for it.
Number 9. Kaluza-Klein Theory. The dimension curled into nothing. In 1919, a mathematician named Theodore Kaluza sent a letter to Albert Einstein. In it, he showed something remarkable. If you add a fourth spatial dimension to Einstein's equations of general relativity, a fifth dimension total, including time, Maxwell's equations for electromagnetism fall out automatically. Gravity and electromagnetism unified. Two of the four fundamental forces of nature, both explained by the geometry of a five-dimensional spacetime. Einstein was stunned. He sought on the paper for 2 years before agreeing to submit it for publication. The obvious problem, where is this extra dimension? Why do we not see it? In 1926, Oscar Klein proposed an answer. The extra dimension exists but is compactified, curled into a circle so small, roughly 10 to the power of -35 meters, that no instrument we have ever built could detect it. The Planck length, the smallest scale at which current physics makes any sense. Kaluza-Klein theory was the first serious scientific proposal that our universe contains dimensions we cannot perceive, not a speculation, as a mathematical solution to the problem of unifying fundamental forces. It did not fully succeed, but it started everything that came after it.
Number 8. Time as a dimension, the one we move through without choosing. This one you are already inside. Einstein's special relativity, published in 1905, showed that space and time are not separate things. They are a single four-dimensional structure called spacetime, 3 spatial dimensions plus 1 time dimension woven together. The geometry of this structure determines how objects move, how gravity works, and why time passes differently depending on how fast you are moving. Here's the part that does not get stated clearly enough. In spacetime, everything that has ever happened and everything that will ever happen already exists. The past is not gone. The future is not unwritten. They are locations in a four-dimensional geometry the same way New York and London are locations in a three-dimensional one. You are moving through time the way you move through space, except you cannot choose your direction or your speed. This interpretation, called the block universe or eternalism, is not fringe physics. It's the standard reading of special relativity by most physicists who think carefully about it. Sean Carroll at Caltech defends it. Julian Barber has written entire books on it. The equations do not distinguish past from future. The arrow of time, the sense that things move forward, is something physics does not yet fully explain. You are not moving through time. You are a four-dimensional object whose three-dimensional cross-section we experience moment to moment as the present.
Number 7. String theory's 10 dimensions, the framework that requires everything.
String theory is either the most profound framework in the history of physics or the most elaborate dead end ever constructed. After 50 years, the argument is still open. String theory proposes that the fundamental constituents of nature are not point particles, but one-dimensional vibrating strings of energy. Different vibrational modes of the same string produce different particles: electrons, quarks, photons, gravitons, the entire particle zoo generated by the geometry of vibration. For the mathematics of string theory to be consistent, for the anomalies to cancel and the equations to work, the theory requires exactly 10 dimensions, 9 spatial dimensions plus 1 time dimension. 6 of the 9 spatial dimensions are compactified at the Planck scale using complex geometries called Calabi-Yau manifolds. The shape of the compactified dimensions determines the physics of our universe, the particle masses, the force strengths, the constants of nature. All of these fall out of the geometry of 6 dimensions we cannot see or measure. String theory makes this prediction not as an option, but as a requirement. 10 dimensions or the math breaks. No version of string theory works in 4 dimensions. The problem, and it is a serious problem, is that string theory has not produced a single testable prediction that has been confirmed by experiment. It is mathematically consistent, enormously rich, internally beautiful, and completely unverified. 10 dimensions required by mathematics, 0 detected by experiment. Number 6. M-theory's 11 dimensions, one more than string theory needed. In 1995, physicist Edward Witten showed that the 5 competing versions of string theory that existed at the time were not competitors. They were 5 different approximations of a single deeper theory. He called it M-theory. Nobody is certain what the M stands for. Witten himself has said he left it deliberately ambiguous. Membrane, magic, mystery. M-theory requires 11 dimensions, 10 spatial plus 1 time. The 6th spatial dimension, beyond our 3, the one string theory did not need but M-theory does, is the dimension in which brains exist. Brains are higher dimensional membranes that extend through spacetime. Our entire 3-dimensional universe may be a 3-brain, a membrane embedded in a higher dimensional space called the bulk. The brain world scenario, developed by Lisa Randall and Raman Sundram, proposes that all the matter and energy we observe is confined to our 3-brain. We cannot leave it. Everything we see, every particle, every force except gravity, is stuck to the surface. Gravity alone can propagate through the bulk, the higher dimensional space between brains. This might explain why gravity is so much weaker than the other fundamental forces. It is not actually weaker, it's diluted across extra dimensions. Most of its strength is leaking into the bulk, into directions we cannot point to or measure. 11 dimensions, 1 leaking force, a universe that might be a membrane floating in a space we have no access to. Number 5. The dimension of scale, the axis nobody talks about. This one is different, not a spatial dimension in the physics sense, but a way of thinking about reality that functions like one. Consider this: the universe has structure at every scale simultaneously. Quarks inside protons, inside atoms, inside molecules, inside cells, inside bodies, inside cities, inside planets, inside solar systems, inside galaxies, inside galaxy clusters, inside the observable universe. Each level has its own physics, its own rules, its own emergent behaviors that do not exist at the level below. Some physicists, and the philosopher Henri Bergson before them, have argued that scale is a genuine dimension of nature, that moving from the quantum scale to the cosmic scale is not merely zooming in or out on the same reality, but traversing genuinely different regimes where different laws apply. General relativity and quantum mechanics, the 2 most successful theories in the history of physics, are mathematically incompatible. They cannot both be exactly correct. Relativity describes the very large, quantum mechanics describes the very small. At the interface, inside a black hole at the moment of the Big Bang, they both break down simultaneously. The failure of our physics to unify across scales is not just a technical problem. It may be telling us something about the structure of reality itself. That scale is not just a measurement, it is a dimension of nature we do not yet know how to navigate. Number 4. Imaginary time, the dimension Stephen Hawking proposed. In 1983, Stephen Hawking and James Hartle published what became known as the no-boundary proposal. The problem they were attacking was the beginning of the universe. In standard physics, time begins at the Big Bang. Before it, nothing. No time, no space, no physical laws. The question of what caused the Big Bang has no answer because there is no before in which a cause could exist. The universe simply begins with infinite density and infinite temperature at a moment called the initial singularity, and physics breaks. Hawking and Hartle proposed a way around this. Replace real time with imaginary time near the beginning of the universe. Imaginary time is not metaphorical. It is a specific mathematical operation multiplying the time coordinate by the square root of -1. When you do this in the equations of quantum gravity, the singularity disappears. Time near the Big Bang behaves like a spatial dimension. It rounds off smoothly the way the surface of a sphere has no edge. In imaginary time, the universe has no beginning and no end. It is finite but unbounded. The question, what happened before the Big Bang, dissolves, the same way the question, what is south of the South Pole, dissolves. Not because the answer is nothing, because the question does not make sense in the geometry. Imaginary time is not something you can experience or travel through. It is a mathematical tool that may be describing something real about the deepest structure of time, that our intuition about time having a starting point is a failure of perspective, not a feature of reality. Number 3. The holographic dimension. The universe might be two-dimensional. In 1993, Gerard Atefft, a Nobel Prize-winning physicist, proposed something that sounds like science fiction and is now one of the most actively researched ideas in theoretical physics. All the information in our three-dimensional universe is encoded on its two-dimensional boundary. The holographic principle emerges from the physics of black holes. When matter falls into a black hole, the information about that matter is not destroyed. Hawking radiation carries it away, but the information is not stored in the volume of the black hole. It is stored on the event horizon, the two-dimensional surface at the boundary. Atefft extended this to the entire universe. The maximum amount of information that can exist in any region of space is proportional not to the volume of that region, but to its surface area. 3 dimensions of space may be a projection, the way a hologram projects a 3-dimensional image from a 2-dimensional surface. Juan Maldena's 1997 paper made this mathematically precise for the first time. The ADS-CFT correspondence showed an exact equivalence between a theory of gravity in a 3-dimensional space and a quantum field theory living on its 2-dimensional boundary. Gravity itself, space itself, as an emergent phenomenon projected from a lower dimensional reality. The dimension you think you're sitting in may be the projection. The real thing may be flat. Number 2. The quantum dimensions, where particles exist everywhere at once. This is the dimension that is hardest to fit into any intuitive framework because it does not behave like a dimension at all in the ordinary sense. Quantum mechanics describes particles not as objects at specific locations, but as wave functions, probability distributions spread across space. An electron is not at a specific place before you measure it. It exists in a superposition of all possible locations simultaneously. The wave function has amplitude, probability, at every point in space at the same time. When you measure the electron, it collapses to one location. The act of measurement forces it to choose. Some physicists interpret this literally. The electron is genuinely in multiple places. Reality has a degree of freedom, a dimension, that corresponds to the space of quantum states, Hilbert space. The mathematical space in which quantum wave functions live has infinite dimensions, not 2, not 10, not 11, infinite. In the many worlds interpretation proposed by Hugh Everett in 1957 and increasingly taken seriously by physicists today, the wave function never collapses. Every possible outcome of every quantum measurement occurs. The universe branches. Each branch is a parallel world where a different outcome happened. Every quantum event, every decay of every atom and every star in the universe, spawning new branches continuously. The dimensionality of reality in this picture is not a number, it is a structure that grows every time a quantum measurement occurs anywhere in the universe.
Number 1. We do not know how many there are. The real answer. Here is the honest summary. We live in 3 spatial dimensions plus time. We are certain of this from direct experience. Everything we can see, touch, or measure exists here. Beyond that, genuinely unknown. String theory requires 10. M-theory requires 11. Kaluza-Klein required 5. The holographic principle suggests our 3 may be a projection of 2. Quantum mechanics in its most rigorous interpretation implies infinite. None of these are the same number. None of these frameworks has been experimentally confirmed at the level of extra dimensions. The Large Hadron Collider at CERN has been searching for signatures of extra dimensions, deviations in graviton behavior that would indicate gravity leaking into the bulk. So far, nothing. The dimensions predicted by string theory and M-theory are compactified at scales so small that no instrument we have or are planning to build could detect them directly. We are 3-dimensional creatures trying to count dimensions we cannot enter, cannot measure, and cannot visualize. Our mathematics tells us they should exist. Our experiments have not found them. The gap between those 2 statements is one of the deepest open problems in physics. The universe may have 3 dimensions, or 10, or 11, or infinite. We have been building the tools to find out for 100 years. We are still building them. 10 dimensions beyond the 3 we can see. From the 4th spatial axis you cannot point to the curled-up geometries of string theory. From time as a structure you already live inside to a universe that may be a 2-dimensional projection. From the mathematical requirement of 10 dimensions for the physics to work to the infinite dimensional space of quantum mechanics. None of them confirmed, all of them serious science, all of them pointing at the same possibility, that the reality you can perceive is a small slice of a much larger structure. We see 3 dimensions. The equations keep asking for more. Subscribe to Cosmic Hives. See you in the next one.